So this is a joint work with Gabriel Dospinescu, which is still work in progress. So most of the theorems I'm going to state today, they may be not written now, but at least I'm confident, and Gabriel as well, that they are correct. So let me start with a couple of notations. So the first, let F with some fine extension of QP. Let me just take D over F quaternion algebra. That. So the goal of this talk is to study the functor of Scholze of periodic Jacquet-Langlands in the realm of local analytic representations. So we say periodic, everything is periodic. And in between the study of this functor that I will probably recall in a second, these let's say correspondence, actually equivalence of D modules will appear like naturally. Okay, so I hope this is not bad. So let BC is some derived closure. Complete algebraic closure of F. So I'm going to consider Drinfeld space, the geometry, the C point of the C extension of the Drinfeld space. So P1 of F over which GL2 of F will act. Drinfeld space has a kind of a universal cover, at least a GL2F equivariant universal cover that I will call maybe just M infinity, just the I don't know, perfectoid Drinfeld space. For which I have a map that I'm going to call pure state. That is the star torsor. So it's a torsor in the prototype side of Drinfeld space for the units of the quaternion algebra, and also is G of 2F equivariant. So, well, this space can be constructed by some modular problem of p-divisible groups that I may not need to talk today. What I need to talk today is about the other arrow you have from this space, coming from this duality of proportion spaces that goes towards, well, a priori will go to a Lubin-Tate space, but let me take the actual complete quotient of this action. That is going to go towards P1 again, that I'm going to index by Lubin-Tate, and maybe this P1 I'm going to index over Drinfeld, just P1 coming from the Drinfeld side. All of them are coming over C. And this map that I'm going to call P cross-eddy messing satisfies the following properties. So this one, well, in this space, we have an action of GL2 of F and the units of the quaternion algebra. I'm going to forget about the Galois action for now. This arrow is constructed as the quotient by D star and still has an action of GL2 of F. And we can actually perform the quotient on the other side. So this one is going to be a GL2 F torsor. And it's going to be a D star equivariant map. Okay. So in other words, let's say that working in diamonds, this diagram actually endorses a formula, an equality, which is kind of beautiful equality, saying that the quotient of P1 by the units of this quaternion algebra is equal to the Drinfeld space divided by GL2 of F. So say at least the diamond version of all these guys. Just leave that a second. So let me recall what is this theorem of Scholze and what is this Jacquet-Langlands functor of Scholze. So definition. Let P be an admissible maybe unitary Banach representation over GL2 of F. So I'm going to state the Banach version of the theorem of Scholze and let F of P, well, one of the quotients is actually a GL2 F torsor, so we can, from a GL2 F representation, actually cook up a prototype sheaf. Be the associated prototype sheaf. Then we define this Jacquet-Langlands functor, Jacquet-Langlands phi P, to be the prototype homology of this sheaf, which since this sheaf is the D star equivariant object over this guy, you actually have an action of something here. So probably you could define just taking homology groups, but I prefer to stay in this derived setup. So the theorem of Scholze, at least one part of the theorem of Scholze, says that for P as before, this guy is an admissible Banach representation of T star. And maybe let's say this statement this is a derived object, so maybe just let me put this in quotes because this is not actually Banach vector space, but let me just say that these guys are actually, so these guys, which is just the homology of the sheaf, are Banach representations and admissible. Okay. So a second statement that comes into this one is the almost purity for these guys. So when we tensor ULP with C over Q, and well, let me say just a complete tensor product in a suitable sense, this is actually computed the homology of P1 of this Banach sheaf, which is a Banach sheaf in the prototype site, after you maybe tensor with the structural sheaf, the completed structural sheaf in the prototype site. Okay. So now, since I state this theorem characteristic 0, there is a natural procedure that allows the study of locality of admissible representations characteristic 0, which is the passage to local analytic vectors, as we saw in the talk of Eugen. A natural question arises. The question is this functor, let's say, compatible in a suitable sense with local analytic representations? So in this talk, I'm going to give some affirmative answers to this. Or let's say in at least two different flavors, like in from two different points of views. Maybe still related, but from two different directions. I don't know. Maybe this is not correct. More or less the same question in just written in maybe this answering two different properties of these guys. So for doing this, maybe let me first introduce some notation that I will use through the talk. Particular, well, we have local representations. It's better that we can actually differentiate them. So I need notation for the Lie algebras. So some notation. First, I will call the Lie algebra of DL2 of F. I'm usually going to denote it G of G. The Lie algebra of the quaternion algebra, I'm going to denote it G of D. I have the center of the enveloping algebra that I'm going to denote set of G. I think that is kind of a standard notation. And similarly, I also have the center of the enveloping algebra of the quaternion, of the units of the quaternion algebra, this side. And finally, maybe this is there's no standard one. So for B, let's say p-adic representation of a p-adic group H, I'm going to denote BHLA or just BHLA and say it's subspace of local analytic vectors. So for example, if I have just a Banach representation, then I take the usually local analytic vectors as Schneider-Tetelbaum or Emerton or different classical approach. Maybe also for locally convex vector spaces is not too far from what classically is understood, that is local analytic vectors. Since the objects we're going to work with are quite derived, we need to make sense to this notion in a different world, and for this one can use condensed mathematics, and let's say that these p-adic representations are understood in the framework, and these passage to these local analytic vectors are understood as in the joint work with Joaquin Rodriguez, where we start like, I don't know, developing this theory. But just keep in mind that, for instance, if we apply, maybe it's going to do this remark. Oh, no. Good. So since I already introduced this Jacquet-Langlands functor, let me just do a remark in theorem. Remark. Let's say that if V is a Banach admissible representation of H, then these one are just the usual analytic vectors. And maybe in this functor of Jacquet-Langlands, if I as before, then actually I can take this functor to this complex. And when I take the HI of this complex, this is just taking the cohomology group of pi, and just taking this, which is an admissible representation, and just taking the local analytic vectors of this guy. So at least for complexes of Banach admissible representation, this is not doing so much. It's just a formal procedure to actually work in a better, in actual derived framework. But intuitively, not much is changing in with these guys. Okay. So the first theorem that we prove regarding the compatibility of these local analytic vectors and the Jacquet-Langlands functor is that P is as before. Then you can take this guy, take this local analytic vector for this star, which is the action that you get. And this turns out to be the Jacquet-Langlands functor of the local analytic vectors of G02 of F. Moreover, under the identification of the center of the enveloping algebras, maybe after extending the scalars, both centers actually in the same way. So not just we have this compatibility with the passage to local analytic vectors, but actually the action of the centers in both sides, the correspondence, are given by the same character, if whenever one is given by the same character. Okay. So am I going to mention what are the key ingredients in the proof? Okay. So the key ingredient to prove this is, well, another theorem that involves the study of these passage to local analytic vectors in the period shifts of this perfect Drinfeld space. Did I change this? I didn't, right? Yes, so I can change to this. Yes.
Could you define JL by assuming GL2 here?
Yes. Yes, I say just for my representation, but let me say that with a little bit of salt that for any more of a reasonable p-adic representation of G02 of F, you can actually just define a prototype shift by descent to this torsor, and this works. Okay, so the theorem that also with Gabriel and me. So let me first take one. So let's O hat infinity. So this is the structure sheaf of M infinity, so of the perfect Drinfeld space, for which locally we have an action. So of this one, of this group acting in this sheaf, at least locally enough, we have an action of compact groups and we have a coherent action over the whole space. Then as sheaves over the topological space defined by the perfectoid Drinfeld space, we have that when we look at the action of the periodically groups, this is basically a Banach sheaf. We can again take these local analytic vectors for these two groups, and actually they both coincide. So let me call the sheaf just as OLA M infinity. And well, at the beginning, I say that everything should be taken derived. So these one are like honest sheaf. So even if you do the derived definition of these local analytic vectors or something like that, you only get a sheaf which coincides with the usual local analytic vectors in the classical point of view. And also here, let's say that moreover, the actions of both the Penelope algebras are the same. Of both infinitesimal characters, I'm sorry. Yeah. I always work over C here. Yes. And maybe over QP bar just to also make sense for the usual Jacquet-Langlands functor over pi over P. Okay. And also, maybe this is a first version of this. And the second that I may not say it too many details is that at least for other sheaves, E over I arising from the curve confusing French, English. One of the two, the one that actually fits in this language. Okay, so the local analytic vectors of these guys actually can be are the same as the local analytic vector for these guys. So what I mean this is I have a period sheaf depending on maybe some parameters arising from the curve. This period sheaf is going to define a, let's say, a topological sheaf or sheaf over the infinite level Drinfeld space. And well, again, I can ask the question about taking these local analytic actions, and it turns out that both are the same. Let's say that in this case, I don't know if they are just degree zero, so this has to be taken as actual derived sheaves. Maybe the case that they are just sheaves in degree zero, but something that I have no idea. But still, you can prove these kind of things somehow. Okay. So, okay, I just replaced a random theorem with another random theorem. So let me give something that makes a little bit more sense. So why this theorem seems to be reasonable, maybe. I want the other one. I think, right? No, I want this. Yes. Yes. If you do it around this Galois fixed point, then maybe if you do it for Theorem, then well, you should change locally for pro-local analytic. And in this case, actually, this sits in degree 0. This case. So yeah, in this case, you can actually specialize to this map, and this should be kind of surjective. And this is not. I think it should be surjective. Okay, so to prove the previous theorem, like we need 2 inputs. Maybe the first one is a lemma that comes in this theory of local analytic representations. So let H be a periodic group, maybe compact. And let V plus be a periodically complete representation of H. So for example, you can take B plus to be the lattice in a Banach representation. But actually, this object can be also a complex that is periodically complete. So it could be a complex of lattices of Banach representation, for example. Suppose that the action of H on B plus mod P, when I take the right quotient by P, factors for a finite quotient. So in other words, that when I restrict to a finite an open subgroup of H, the action becomes trivial, meaning that it's just the induced trivial action in a complex. Like that. Then actually H acting in the generic fiber of this guy is local analytic. So this is somehow, this is not far from being actually an equivalence, more or less. So this is saying that when you take these these analytic vectors, you are somehow just looking at lattices of Banach representations, so these Banach representations, for which the action of the group is quite small. Small in the sense that when you go down in the natural filtration, the P filtration of this group, maybe if it's pro P, then actually the action of these subgroups becomes exponentially close to the trivial action, which is some more or less related with, like more or less equivalent to this result. But the mod P, the action is actually trivial and factors to a finite quotient. Of course, in general, you have a Banach representation in lattice, the mod P action is just smooth. For instance, in completed cohomology, the action modulo P is just smooth, but it does not factor to a finite quotient. So that is more or less the big gap between the local analytic and the usual continuous Banach representation. So we have stronger conditions in this, this kind of condition in the action. And the other ingredient is a theorem of Saviolov. Saying that if U is SPAO A plus, it's smooth over C, then let's say that H acts on U, periodically group acting in this rigid space. Then well, actually this doesn't matter in the end. This is something to use. then the product homology of U with coefficients in O hat plus is almost coherent over A plus. I think this is what the theorem says. So in other words, the way you use these both statements to prove such an equivalence relates to, let's say, just going to write it here, like these two things are going to imply that if H acts on U, then the action of H in this homology almost factors maybe mod P to a finite quotient. So in other words, whenever I kill a small power of P, actually the actual action is going to factor through a small quotient, meaning that actually when I go to O hat itself, the action is going to be locally analytic indeed. So this will imply that we're going to write it on the board just here actually. I forgot.
I find some locally analytic representation.
Yep.
And this is given by a family of norms.
Yep.
And if I complete this with respect to one of these norms and take a Laplace with respect to it, I thought something like this happens if I just want to here, I can actually define
I mean, a local representation is usually a co-limit of Banach representations.
So I take one of these Banach.
One of the Banach representations, actually, this property holds.
But this Banach representation is from
It's analytic, even for some radius of analytic. I mean, maybe if this Banach needs to be stable on the direction of H, and maybe. Yeah. Yes. So let's say that these theorems, again, the implication, they will imply, for instance, that the action of H in the product homology, I mean, maybe this is not too hard, of O hat is local analytic. Let me say that with some work, actually the action of H in the product homology of U with coefficients in QP is also locally analytic. Okay, so all the statements are more or less related to these two guys upstairs. Okay. Any questions? It means in this solid sense of being local analytic representation is, I mean, in this case, you could, and this is something that I'm not sure about now. Actually, maybe. Is it what? Yes. Yes. So there is this notion of derived local analytic vectors that is introduced in the paper with Joaquin. And in this notion that this makes sense in the category of solid representation of H, then actually being local analytic means that it is equal to its local analytic vectors in this category. They just continuous solid representations, just solid representation of H. So for instance, I mean, these guys are, of course, can be something quite abstract. The homology groups not need to be separated, for instance. I don't know what they are. But still, this notion makes sense for this complex and actually is going to be local analytic. But the point is that, I mean, like globally, if you work with proper or maybe these other spaces, you get nice shifts for which you can recover more classical interpretation of these local analytic vectors, for which is something reasonable to work with. But in order to localize problems and to use, let's say, the geometry of these spaces, you need to enlarge the category of local analytic representations and allow these sort of derived representations for them to make the arguments. Hold on. I can do a side for this. So let me just first recall what the definition of local analytic vectors are, and then just put an R everywhere. So H, a periodically group acting maybe in V in a Banach representation. I can take the space of local analytic functions of H with values in V, right? This is just functions on H with V, which has some power series developments. And I can take an action of the group in here. So H acting here as follows. So G is going to act in a function of H by taking G minus 1J. So this is just an action that basically, when I take invariant vectors, I only take orbits. So it's an action. Yes, but then I just going to change a couple of things and everything will become the same definition. That sees orbits. Then the local analytic vectors, in a classical sense, is just the invariants for this action with an H, right? The invariant for this action. More generally, if V is a solid representation of H over QP, then these local analytic vectors, I mean, again, I first need to tell you what this is space of local analytic functions. This is actually easy. I mean, take the local analytic functions of H, and then you may need to take the solid tensor product with V. So this is just a complete tensor product in a suitable category. And then I told you to take H invariants, and then you do exactly the same thing here. You do the H invariants, maybe with respect to the action of the Wasawa algebra. Of this gadget. So it's just the same definition, except that you derive in any kind of formula you can write down for this guy. And if these Banach representations, this could be a complex, but the H naught is just the usual space of analytic vectors. It is an admissible representation. This actually is concentrated in degree 0, and it's just the usual space of analytic vectors. Should I change the board? No. Okay. So yes, whenever I say something is local analytic, it's referred to that definition, weird definition, right in there. Fortunately, theorems make sense now. Okay. So now I say that this functor of Scholze is compatible with the passage to local analytic vectors, at least for Banach representations. Now, another equation that arises afterwards is question 2. Is this functor, let's say, preserving admissible locally analytic representation? Okay, so it preserves admissible Banach representations. One could wonder if it actually does the same for these local analytic ones. And maybe a first answer to this, which is a boring answer, the boring one, is no, because already if phi is just an algebraic representation, then this Jacquet-Langlands functor of pi is actually a Banach-Kolmogorov space. But what I say that this is a boring no, because maybe the question is not formulated in the correct sense. So better question. So expectation maybe is that this Jacquet-Langlands functor of pi should be the global sections of an admissible local analytic representations of D star, but now not over QP itself, but over the Farfontaine curve. Okay, so say that should be a definition of admissible local analytic representation over this guy, basically saying that it's admissible relative to the sheaf functions of the Farfontaine curve. And the fact that when we take global sections, we get spaces that are quite big is just an incarnation of the fact that maybe the spaces, the shifts that we end up in there, they're not étale. They may have some slopes, which make these Banach-Kolmogorov spaces appear. So maybe we'll give, how much time do I have? Okay, good. So I will give maybe some evidence for this. How? Well, I told you that this should be admissible Banach representations, admissible local representations over the curve. So in particular, when I specialize in the Galois equivariant, Galois fixed points, so in theta equals to 0, I should find admissible representations over C. So in other words, I will need to work with O hat coefficients instead. So at least working with O hat coefficients, the theory we have now kind of allows you to prove that actually this admissibility property is going to be preserved, maybe modulo some work that is not yet written up. But anyway. Okay. So to make this work, then we need to consider funny objects. In particular, we need to consider a funny sheaf that was firstly considered by Dupin in his work of local analytic completed cohomology and the modular curve. And let me just write the definition of the sheaf. So the definition, maybe first consider by Pan. So we want to study these local analytic representations. Again, the idea is always to try to localize the theory to use sheaves and then try to do as much as you can with the sheaf to obtain global properties. So we can do exactly the same here. So as I wrote before, probably I should have written this before. Was Pan the one that first considered this kind of objects. So I'm going to consider this thing that I say that is the same for GL2 of F. And D star of L. And well, maybe this is not exactly as Lue considered these things, but let me just define the following. Let me just say space. And let me not put too many adjectives to the space. So it's just going to be well, maybe let me just say that usually M infinity can be thought as a locally ring space given by the topological space and this sheaf of functions then I can do the same, considering this sheaf and this sheaf of functions instead. Okay. So now, recall that I have two maps to the Drinfeld space, which is inside a Drinfeld flag variety, pure state. And I have another map, the Lubin-Tate space, that I call the figure of the dimension. So that the action of both groups in each side are actually locally analytic, because it's just actions in algebraic varieties. Even one of the actions in each side is smooth. So actually, this map are going to factor through this space. Maybe let me do a warning. These guys when you take these local vectors are not torsors anymore. At least not torsors for the groups pretty much anymore. Yeah, actually something more funny will happen with them that hopefully I will explain in some minutes. That why it's important these guys are not torsors. Yes, so okay. So let me just say that in the diagram we had before, when we saw each space as a quotient of M infinity, we actually considered all these spaces as diamonds. So we saw a different incarnation of a rigid space as a diamond. In this diagram, we actually consider both rigid spaces as actual rigid spaces somehow. And this M infinity LA is again not a diamond. It's not a diamond. It's more or less considered as an honest space with that sheaf of functions. Okay. So to continue with well, I never mentioned the modules, so I should introduce them now. For introduce these D modules, actually, I need some notation coming from the Lie algebras. So let me maybe just say that I have a site here. So we have the, I don't know, Lubin-Tate site. We have the Drinfeld site in here. So here we have a flag variety. And maybe from what follows, for simplicity, let me just focus for F equal to Cupid. Already many of the ideas are in this case, so I don't complicate my life. And here I have a Drinfeld space like that. So recall that the way we think about these flag varieties is as GL2 divided by some Borel subgroup. And this one is, well, maybe I take the extensions to C of the quaternion algebra, and I want to divide maybe by the opposite Borel instead. So this is because in the duality of rapporting spaces, the Hodge and the Hodge-type filtration are kind of going the opposite sides. So already called the Lie algebra of this by G of D. So I have an action P1 of Lubin-Tate. This induces an action of differential just derivations over the structural sheaf of P1 of this projective space, which is the same as having the so-called anchor map from this Lie algebra towards the tangent space of P1. So the tangent space is just space of vector fields that acts in the structural sheet by derivations. And since I have a derivations of G just coming from the natural equivariant action, I have a map like this. This is actually surjective. Inside of this guy, okay, so I have the same kind of thing on this side. Into space. So because I have this representation of a quotient of a group by another group, actually equivariant bundles in this sheaf arise as representations of B bar. So inside of this representation, actually I have some other subalgebras that arise say that are induced from that joint representations of B bar, or maybe in more precise terms, these are just algebras that are constructed by taking the Borel subgroup that takes each point and its unipotent radical, respectively. Similarly, I have this kind of algebras inside this diagram, and what's like that? Okay. So now I will define the sheaf of differential operators that make the word E model appear. I don't know where this microphone is. Just there. Now definition. Again, from the Lubin-Tate side, and we also have a Drinfeld side. But first, I can define the actual differential operators of the P1. And these guys are going to be constructed from basically differential operators arising from derivations. Derivations are just the action of the tangent space. So it's just enveloping algebra relative to the structural sheaf of the tangent space. But this actually can be also obtained as enveloping algebra of this quotient. So this is just because this quotient I wrote here by the subgroup is just the tangent space. Let's say that this can be more or less seen from the fact that the Planck variety is just G over B. So you will expect the tangent space of G over B to be G over B somehow. You can also consider a twisted version of these guys. Doing so, you are studying families of differential operators of line bundles over the Planck variety. And this is just enveloping algebra of G naught divided N 0 naught. This is just all differential operators of line bundles. And this one is just the differential operators of the projective space stuff. And similarly, let me just define these things very quickly. So you have this. I should put a D in here and a G in here. G over B and not. Okay. So now D modules are just quasi-coherent sheaves endowed with an action of these enveloping algebras. And well, this is actually what I'm going to write now. So now, a definition. Well, maybe this is some notation more than a definition. I will let B cross acts in the Lubin-Tate space of P1, and maybe, and I can consider D modules with a D star equivalent action. So this is a space of, and let me put this in parentheses, solid local analytic too many adjectives, D equivariant. D modules. So, for instance, any vector bundle that has an action of this connection, twisted connection, and the equivariant action for the quaternion algebra actually is an object in here. But also you can find more funny things like localizations of admissible representations of the cross into the flag variety. And also, I can consider the same thing for the Drinfeld space. So this is the same solid local analytic space of solid local analytic GL2 of QP equivariant D tilde modules. Okay, so why I'm telling you about the spaces, because of the following theorem of Pan that was then generalized my thesis, is that, well, we still have an action of each of these n knots, n bar knots into these local analytic vectors of the Drinfeld space. And actually, this action on each unipotent guy in here is trivial. That's trivially. Again, I have an action of the Lie algebras that I can then just make an action of the actually these Lie algebroids over each space, and I can restrict to the action of each unipotent subalgebra, and the action of each one of these guys actually is going to be 0 in this guy. So in particular, I have an action of D tilde Drinfeld and D tilde Lubin-Tate over OLA anything. So since I'm about to finish my time, I have 2 minutes, then I'm going to finish stating, oh, this went too far, the theorem that relates D modules from one side and the other side, that comes thanks to this equality. So come write down the theorem. Okay. So there is a functor let me just call it Jacquet-Langlands D tilde that goes from this GL2 of QP equivariant D tilde modules over Drinfeld space, big name, and goes to this D star D tilde here with the Drinfeld here Lubin-Tate modules over the P1 of L. And actually, well, I will write the functor at the end. I just want to property of this functor. So this functor is an actual equivalence of D modules in these two sides. And moreover, if pi is an admissible, or maybe pi is a local analytic representation of GL2 of QP, then when you apply the functor of Scholze to pi, maybe the version with O hat coefficients to the functor of Scholze, this is actually the same as taking global sections in the analytic topology of P1 of this Jacquet-Langlands d tilde functor of the localization of pi to the flag variety, or maybe to the Drinfeld space. Modulo maybe a shift, a twist that I'm not able to write down now. And second, and third, is that if pi is admissible, maybe F is an admissible or coadmissible, coadmissible D module. So GL2F QP D tilde module over Drinfeld space. Then this Jacquet-Langlands functor, maybe the globe, this Jacquet-Langlands functor of D tilde of F is an admissible or coadmissible. The equivariant D tilde model. So this Jacquet-Langlands functor is also preserving admissibility. And let's say that since P1, so it's a consequence, P1 is proper. Actually, the Jacquet-Langlands functor of P tensor O hat is locally analytic admissible for pi admissible, local analytic admissible. Okay. So I think that my time is over. I finish. Thank you so much.